All right. Well, good afternoon, everyone. Yeah, I'd like to thank the organizers for inviting me. I'm very happy to be here. So in this talk, I'm going to present some of the research topics that I and my colleagues in Ericsson Research have been working on towards for 5G, and for which we use information theory to solve them. Okay, so don't go home yet. This is joint work with Songnam Hong and Dennis Hu in Ericsson Research and Giuseppe Caire at TU Berlin. Okay, so being the last speaker of the 5G day, I'm not going to give you an overview of 5G. I'm just going to point out a few facts about 5G that led us to work on these topics that I'm going to talk about. And then I'm going to present two topics. First, I'm going to talk about multi-hop communications for 5G, where these scenarios arise, and what is the scheme, what are the strategies that we developed or proposed for 5G. Okay? And then I'm going to talk about the polar code, so it'd be like a continuation of the talk that we heard this morning by Bin, and actually I'm going to talk about the rate-compatible polar code, the solution that we proposed. Okay? And I'm going to divide my talk into equal parts, about 15 minutes for each. All right. So, we've heard this a little bit in this, well, in detail from John and Farog this morning. So every new generation of cellular brings something new. We went from analog to digital, from TDMA to CDMA to FDM. So what is new in 5G? And one thing, as John described, we have many new applications. So it's not just that we need higher data rates and better coverage and better reliability. We do. And that's what is referred here as enhanced mobile broadband. But then there is many other applications that we want to serve with this new system. And what they bring in, why we care, is that we have all new set of requirements, right? As also we heard. So we want we'll have much more data, bigger volumes, higher data rates, lower latency. We need lower latency and so forth. And what we want a system that can now provide for all these requirements. Now, not each application will need all these requirements to be satisfied. Rather, we will have application that needs to be very low latency and the other one that is very high rate, right? So now we have to provide for these different applications. And we want to design systems that can serve them all rather than making little network that can provide very low latency and so forth, right? So we want, in designing the 5G, we want this common network platform that then can be a bridge for all these applications, right? So it's bridge, you get it, right? So here are some application examples. We've seen some earlier. So of course, broadband, one that we are looking at in Ericsson Research is personalized TV. And the big focus also there is on machine-type communications. Okay, that's what we call it. So there is and this is like going towards IoT. There is two types of MTC that we are looking at. That is massive, and here is an example of monitoring of the infrastructure. And then a critical MTC, where we are, in this example, we are controlling some heavy equipment remotely. Okay? So the two types of MTCs, the machine-type communication, are, as I said, massive MTCs. So you can think they are characterized by a large number of devices, a small amount of data. We want it to be low cost and low energy. So you can think of, like, for example, sensor networks. And then the other is critical MTC, that we want really ultra-reliable, extremely low latency. And here are some examples. These are the self-driven vehicles in the factory, or controlling of some processes in industry, or control of the smart grid, or even the remote surgery. So you can think that for this you really need very reliable communications. Okay, so what are the solutions that we are looking at? In particular, in the group that I work with, we work on the physical layer. So what are the physical layer solutions that we are looking at? And again, this is ongoing project, right? Ongoing research for 5G. So there are many, and I'm going to show you some that we are working on. So of course, we need higher data rates. We have to extend to higher frequencies. We've heard that today several times. And then the other is small cells. Massive MIMO, we just heard a very nice talk by Tom. Multi-hop communications, channel coding, as you heard, and energy efficient design. Since we'll have more infrastructure, we really want to be careful and to be as energy efficient as possible. So we are designing the 5G with that in mind. Okay. So today, as I promised, I'll talk about multi-hop communications and channel coding. And I'll just say a few words about this extension to higher frequencies, how that, and to show you how that leads actually to multi-hop communications in some cases. Okay. So as you heard, right, if you look at the 5G spectrum, we're extending to higher frequencies, and we have two different designs in mind when we talk about the lower frequencies, which are denoted here as cellular access, and then higher frequencies, which is the millimeter wave. So for low frequencies, we have more like a standard cell approach. We'll have we want to provide high rates and wide coverage, so we'll have microcells that are carefully planned infrastructure. And then for millimeter wave, what we want is really to cover more like a high spot, so we'll have the low complexity small cells. And then what we get together is a heterogeneous network, right? So that brings a lot of also research topics, how now you handle interference in such a network and so forth. Okay. Now, if we look what happens in the millimeter wave bands, what we expect will have a dense deployment of small cells. Okay, and it's for two reasons. One, because we have more attenuation, so we have to bring the cells closer to each other. And the other is that's the way to increase the throughput, right? We'll put more infrastructure, we will have higher data rates, right? So, and the reason I have this picture here, it's nice, but it's also to show that what we expect is that we'll have these small cells on the top of the buildings or the side of the buildings, and a lot of them actually indoors, like in every room, in the outlets and so forth, okay? So one question, if we have all these small cells, is how do we do backhaul? How do we provide connection to all these access points from and to the rest of the network? Okay, not to the users, but to the rest of the networks. And traditionally, how backhaul is done, we have to the microcells, we have a point-to-point high-capacity links over that are typically line of sight. But this is not possible if we have now a large number of access points. Right? So one way is, again, to have the fiber grid, but that brings some overhead and therefore increases cost. And also we want to be flexible. The small cells can come and go, so we want to have flexibility. So another solution that doesn't have to be competing, can be complementary, is to have wireless backhaul. Meaning now we will, to this access points, we will send the data wirelessly, and they can actually be relays to each other. Okay, so they will not just serve users. Actually, John had a picture this morning of that, where access points that not just serve users, but it actually is a relay for another access point. Okay, so here is a very small example where we have this, what we call aggregation node, which is the node that has connection, the wired connection, and it's now wirelessly, which is indicated with these red lines, serving these access points. And here you can see this access point is now relaying data for this access point. Okay? Then if you now look what is the underlying channel model, right? What we have is a network with some sources of information. They have these little tails to indicate that wired connection. And we have these users, and in between we have the network of access points that can now serve as relays. And the question we want to answer is, well, what is the efficient communication scheme? What should these relays do? Okay, so that is the problem we'll be looking at. Okay. Now, if we cast this in the language of information theory, what we have is this network with, say, k users, right? And in general, we can assume that any user has a message, which I denote here as W, to send to another user in this network. So WI is the message at node I. And the node sends that by encoding into the input to the channel, which is XI, and what it observes is YI. Okay? And then the whole channel, this multi-user channel, is described by this probability of all the outputs given all the inputs. And then one question that multi-user information theory is concerned is, what is the capacity region of this channel? That is, what is the highest set of rates that are simultaneously achievable for all these users? Right? And the smallest network of this form, the simplest, is of course the relay channel. So in the relay channel, we have one source only to communicate to only one destination, and there is one node that is just helping this this communication for that single source-destination pair. So it doesn't have data of its own, right? So source is sending W to destination. And so this channel, we don't know the capacity even of this channel nor of the big network, right? And if we look, the multi-hop research on multi-hop in information theory started with the introduction of the relay channel by van der Molen, which was back in '71. And the fundamental schemes that we have today were proposed by Kovar and Gamal back in '79. So information theory has been looking at this problem for a long time. And it's true, we don't know still the capacity, but we understand a lot about the multi-user settings. Right? So we have efficient multi-hop schemes. We know that they achieve capacity in special cases. We know they give us the inner bounds. We know the outer bounds, so we have the bounds. We know the gap to the capacity. We know the scaling laws. Okay? So if we look at that scheme, they did not, however, have much practical impact. We don't see these ideas coming to practice. Right? There are examples of using relays in 4G, mostly for coverage, but really they didn't take off. Okay? So why is that? So one reason might be that some of these schemes are too complex, okay? And I will talk about complexity of these schemes a little bit later. The other reason is maybe there was no need. You know, we built a good networks in previous generations that were using uplink and downlink, and there was not that much of the multi-hop communications or need for them. So there was no need to bring these ideas for theory into the practice. Okay? But what we see instead, that in 5G, we will have multi-hop communications, right? So one example, as I shown before, is this multi-hop backhaul, right? So this here is another like extreme example of it, where this is a Giants parade in San Francisco, and you can think that that in this case we'll have a large data volume, so we'll need a lot of small cells that are on the, on the bus stops, on the poles, and so forth. And for these small cells, we will need a wireless backhaul. That is multi-hop. The other examples is in MTC, in machine-type communications. These are the use cases that are considered for 5G today, and these are the volumes of traffic that are expected. So this is the marathon. This is some event at the stadium, or soccer game, or a match, or the football game, and this is a traffic jam. Okay? So what all these pictures have in common is that their underlying model is this multi-hop setting. So what we would like is to bring some of these ideas from information theory to solve these problems. Okay? So that is what we've done. So let me show you some of the elements or ideas that we used to solve this problem. So the relay schemes that we looked at are the relay schemes, of course, from information theory, and there is two things you can do with the relay, right? You can decode and then forward it. So for that, we have a scheme of decode and forward. Or not, you don't decode. And there is various ways in which relays can help without decoding actual message that the source sent. For example, it can amplify and forward. The one we looked at is the one in which the relay quantizes, okay? And then forwards. So again, the scheme for that was proposed by Kovar and Gamal. It's compress and forward. And later on, different schemes were proposed for a network. So we have quantize, map, and forward. And then its generalization to noisy network coding. And then its variation to short message noisy network coding. So in all these schemes, the relay operation is similar. You do quantization of the observed signal, and then you send out some information about it. But there is some details in which these schemes differ at the encoder and decoder, and that actually determines the performance and the complexity of these schemes. So for example, the last two schemes are similar. They have the same performance, but the second one is slightly simpler. Okay. So both of these approaches, decoding or not, have its advantages. So in the decode and forward, what is nice, the relay will receive the noisy signal. It will decode, so it will remove the noise prior to encoding and forwarding. But the problem is that it imposes decoding constraint in the sense that if the relay has to decode, so the transmit rate has to be below the capacity of the link from the transmitter to the relay. Okay? So if your relay has a low channel, weak channel, that's going to reduce the performance. And the opposite is true if you're quantizing. Because here there is no decoding constraint, nobody is decoding, so there is no decoding constraints, but there is a quantization noise that is propagated, and that reduces the rate. So here is one slide to show you just the idea how the noisy network coding works, or any of these schemes. So as before, suppose the relay receives Y and sends out X. So what it does actually vector quantization, meaning it waits to receive n symbols. N is here the block length, so it receives n channel uses, n symbols. Then it compresses or quantizes into, so that means it determines this Y hat, and then it maps it into another code word X, and it sends it out. So it uses two code books, Y hat and X, and they're both indexed by this what is called quantization index. Okay? And in a moment I'll tell you why then I'm drawing this bigger than this one. Okay? So it's really simple. The relay receives the signal yn, it's a vector, that helps it to determine one of the code books, the entry, that determines this quantization index L. And then it uses L to determine X, and that's what it sends out. So it's quantize, map, and forward. Okay? Now, there is one difference. If you do compress and forward, there is additional step where instead of sending L, you first do what's called Wiener's binning, meaning you determine a bin to which L belongs, and then that's what you encode and send out. So this operation is simple. So there is one more thing, that this whole work is developed for full duplex relays, assuming the relay can transmit and receive at the same time. So if that is true, then you need, that brings a little bit more details to this scheme, that each Y hat has to depend actually on two indexes. One that is in this in the present block B, when it's deciding on LB, but at the same time it is sending out for L from the previous block. Okay, so it's subtlety, but it has to be there if you really have full duplex relays. The complexity is at the destination, because this scheme assumes transmission in B blocks. So source transmits in every block a code word, and then all the relays quantize, and now the destination decodes after all B blocks based on all the code books that I just shown you of all the relays of the source signal and its received signal. Okay? So the point of this slide, and if you don't care about all these details, is that decoder is joint decoder destination, and its complexity is just, you cannot be done in the practice as is. Short noisy network coding has slightly simpler decoder that has joint decoding per block, but then compress and forward actually has successive decoder. Okay, so why am I telling you all this? If you look at the performance, these schemes are the best we have for multi-hop communications today. Okay? We know for noisy network coding, short noisy network coding, they achieve the constant gap to the multicast capacity. Okay? And in general, in general networks, they can outperform other schemes. Okay? So can we use that or these ideas in practice? Right? So in particular, we looked at the multi-hop backhaul, and this is just another example to show you how we can multi-hop through these APs. So is it that proposed? Is that looked at for 5G? Current proposal is to use just routing, and particular interference avoidance routing. So here is an example. I have these two sources. They want to talk to their two destinations. What you do is you establish a route between each two pairs, and the relays perform decode and forward. Actually, it's a simpler version, which is store and forward. So you establish two routes. Now you iterate. You fix one route, and then you find a new route for one of the pairs, and then you repeat. And what you end up with is really these two paths that are as far away from each other as possible. Okay, so this works well in low interference. The problem is it does not work in high interference, which is really high load. And it doesn't work because you cannot just find always two paths that are far away from each other as possible. And even worse, it's enough that you have one relay that is affected by interference, because rate in routing is determined by the minimum of the rates on all the routes, right? And that becomes your bottleneck. It's like a pipe. Okay, so it doesn't work. So we do need something better, okay? And this is the motivation for this work. We need something more than routing. So can we use noisy network coding? So here are the practical challenges to using noisy network coding. First is, as I explained, is the decoder complexity. Okay? So we need a simpler decoder. The other is the relay selection. What is assumed in noisy network coding is that all relays, they listen and then they just compress and forward. And that, it's not really practical. And I don't think this is per se challenge, but because you can come up with many heuristics how to choose relays, but it is a step that needs to be solved if we're going to implement this. The other is the rate calculation. There is no route in noisy network coding. So calculating a rate requires to calculate a rate on each cut in the network. Now, number of cuts is exponential in number of nodes. Okay. So that's another point. And then, as I said, we have full duplex assumption. We still have half-duplex relays. So we will have to look how to use these schemes for half-duplex, which is actually a little bit more complicated problem, because now it brings a new dimension, because now you have to decide for each relay when it's transmitting, when it's listening. And then the CSI. The destination has to know the channel state information, not just for its neighbors, but for the nodes that are a couple of hops away. It has to know generally the channels, CSI for the network. Okay? So all these need to be resolved if this is what we are going to use, right? So I think if we look at the relay selection, I said there is ways we can choose how the relays, the order in which relays should do the forwarding. And one natural way is to have source transmit to its neighborhood, and then these nodes will forward to its union of its neighborhoods and so forth, right? Of course, there are some details there, but that would be the idea, right? So this, you can think of it like generalized routing, right? Because now in each hop you come up with a group of relays that will perform the relaying scheme. Okay? If you do that, then the network that you can look at looks like something like this, right? Now I'm just looking at the relays that are active. Here we are neglecting the interference across the layers, which makes a lot of sense, for example, if we are in a millimeter wave. Actually, this kind of network without this interference is looked a lot in information theory. It's a layered net. It's called layered network. But usually these models neglect this inter-relay interference, and we did not want to neglect that. Okay, so we analyzed this network. Suppose we did the relay selection, and we have a network like that. So the capacity again is not known for this channel. Okay? So we have several different solutions for multiple sources and multiple nodes for relay. I'm going to just show you some of the ideas for the simplest case. So we have just 2 nodes for relay, and we have 1 source destination pair. So what should you do? We don't know the capacity. But here is what we know. So we have this simple network. Okay, suppose relays are full duplex for a moment. This is what is called line network, because each node just hears its neighbor. Then the capacity is easy to see. The capacity is just log 1 plus SNR. This is your cut, right? If you look at your cut set bound, and this can be achieved by decode and forward. So here you're done. You decode it forward, and you achieve capacity. Now we have full half-duplex relays, right? In our case, we want to work with half-duplex. So if you have something like this, so each hop I have 2 relays, like I shown in the previous graph, then again you can actually achieve the same rate by doing the following. You transmit in the first time. These blue nodes denote nodes that are transmitting, and the white nodes are the ones that are listening, because it's half duplex. So source transmits to this relay, and then that is listening. And then in X time slots sends independent information to this relay. Meanwhile, this node is forwarding. Okay, so this is called successive relaying in literature, and it achieves capacity. We get again log 1 plus SNR. But in reality, as I said, we have the interference. We have relay interference. So what is the capacity? So if we do now, here is previous work. If we do now noisy network coding or any of the quantization schemes, how the rate goes down with number of layers from the capacity, it's linear. Linear, and the penalty is because we use this quantization noise level, which I denote here as Q, to be the same as noise, power of the noise. Okay, so then you get your rate that is that goes down linearly from the upper bound. So that's your penalty from quantization. If you do a little bit smarter way you quantize, this is work by Colt and Osger, you get actually a lot of gain. So now your gap to the capacity just decreases as log k. Okay? And you can actually determine optimal quantization. This is work by Hong and Kaire. You'll get the same, same term here, but actually you do a little bit better. I'm not showing here exact expressions, but if you would look at the additional expressions here to have equality, then you'll see that you get gain, especially in high SNR. So what this tells us is that if you should optimize your quantization because you'll gain a lot. Okay? But what we observe is that this rate gap is actually not negligible as k increases. I will show you the curve for that later. And when I say large k, I mean 3 or 4 hops. So k is 3 or 4. Okay? And this is what we will have in our practical scenarios. So our goal was, can we improve this performance? Can we reduce this gap and have a simpler scheme? Because some of these schemes, they need joint decoder. So can we have a simple scheme, simple in the sense that we address some of the challenges that I've shown you earlier and improve the performance? So I'll just show you the flavor of it. So one approach that we use to do that is we use adaptive scheme. That is, using all the relays to do noisy network coding is too constraining. We can instead have relays that have good channel, decode and forward. And that is good because they will eliminate the quantization noise and therefore improve the performance. Because the gap I've shown you is due to quantization noise. So if there is nodes that have a good channel, why not let them decode? Okay? Now, the rest of relays will quantize. Okay? So this is what we call adaptive scheme, and this is not new idea. This was done in the work by Hu and Kramer for a small network with 2 relays. So we generalized this idea, and we added it to that idea another element, which is the rate splitting. Rate splitting used for the same purpose as in the interference channel. That is, if we split the data at one node, then this will allow the relays to decode part of that information and partially cancel interference. So we use it exactly as in the interference channel. Okay? And so this is how we will improve the performance compared to the previous work. Now, we still, as I said, want to reduce complexity, so we will use successive decoding at the destination, no joint decoder. And it actually turned out that with our scheme and in this considered network, we can do that without losing the performance. Okay? So that is nice. And so here is just an example. So I have this network. I do successive relaying as I shown you before. So I send W1 to this node. And then in the next time slot, I send W2 this way. So actually W1 will, meanwhile, W1 is sent from this relay this way. So upper path is send W1, and W2 will travel this path and reach the destination. So each relay will choose to decode or quantize. So here is an example. The red nodes are going to decode and forward. The rest is quantizing. And then we do rate splitting. And then we optimize the quantization level for the reason I told you before, because we want this improved log k reduction to the capacity. And it actually turns out that if that is what we do, then you can do just compress and forward. So you can do binning. You don't have to do noisy network coding. You could, but this is simpler scheme. And furthermore, it allows destination to perform successive decoding. Okay? So I'm omitting some details here why this is the case, but these are the elements of our scheme. So the scheme will be simpler because we'll have successive decoding, but we will have the improvement due to this technique. Okay? So here is an example. So if the source sends W1, the node that is doing compress and forward is just sending the bin index, L. This node is for decoding. So it doesn't decode message. It decodes just the index and forwards it. Whereas this relay that's decoding actually decodes message. So each decoder forward relay will decode whatever was sent from the previous node. Okay, so not actual message. This relay relay number 3 cannot decode the message. Okay? And then the destination will decode successively. When I say successively, I mean destination will first decode what he received from the last layer. Then, given that information, it will decode the message sent from the previous layer, and then finally the message. And at the same time, it will treat what was sent at the other path as a known interference. And that can be done due to successive relaying. If you look now how it works, you'll see that this is the true. And if you do that, then you can see, for each of these steps, you can see what are the bounds of your rate. Okay? So you will not have to calculate rate across every cut. So if you do that, and we did it, you can actually get a closed-form solution for any configuration, which relay does what. Which relay does rate splitting, doesn't matter, for any arbitrary configuration. I'm not going to show you, the expression is complex, so I'll show you the example of just to show you the flavor. So if you have a special case where all these paths have the same, all these links have the same gain, and then these have some other gain, then the rate pair, you have two rates because one for the upper path and one for the lower path, is characterized by this simpler expression, okay. Fairly simple. This is C is given by this log of this expression given by this. Okay? So you can find the closed form solution. Okay? You don't have to go through all the cuts. Okay? And then you can calculate what is the performance, and this is the scaling, how the R goes down with K, which I showed before. Now I'm showing it a little bit different form. So before we had linear for QMF or quantized mapping forward. If we optimize, we had log K. And what we get, again, is log K, but we have this factor in front. This is not scaling. This is exact results. And this improvement is due to the fact that some relays are that there is less relays that are quantizing. And in this example, there was half of them quantizing, so you get this improvement by half. Okay? So this is how you'll get improvements. And here is the general case. So this is K, the number of hops. This is the rate. So this is noisy network or quantized mapping forward with noise quantization. This is, if you do, this is called 10 Osgood result. And this is the optimal quantization. So as I told you, you get a lot if you're optimizing. And then our scheme will give you the red and also the blue, depending how you do decoding at the relay, which I know, whether you do joint decoding at the relay or not. Okay? And then this difference, this is strong interference regime, and then in weak interference regime, these two curves overlap. This is exactly as in the interference channel, because how you treat your interference is not that important if interference is weak. Okay? But the important thing is that we will get improvement, and remind you that we will have a simpler decoder here, where here you will use a joint decoder that we cannot implement. Okay? Whereas this scheme is something that we can actually possibly do. Okay? Okay, so the elements are, we have adaptive scheme, because that will reduce the number of quantizing relays, and therefore it will reduce accumulation of the noise and reduce that gap. We will do rate splitting. We will optimize quantization to get the log K factor instead of K, and we can use successive cancellation. And then there is different ways in which we can do this relay selection. I didn't talk about it. We have this is a heuristic. We have one we call interference harnessing routing. You can think of others. Okay? So these are some elements of our scheme that we think we can use. Okay, so my last 15 minutes. I have 15 minutes. I have 15 minutes, right? Yeah. Okay, I'm going to just say a few words about polar codes. Okay. So this is a continuation of what we heard. It's very related to the talk we heard this morning by Bin. So, in LTE, we use turbo codes there, right? And so the question is now, going forward, why, first of all, we need to look at, do we want to look at other codes? And when we decide on that, we take into account several considerations. We look, of course, we look at performance, we look at complexity. By complexity, I mean processing. That is how much processing we need per bit. What is the memory that is required? What is the decoding throughput, meaning how fast the decoder can output the bits? What is the energy efficiency? And what is rate compatibility? Okay? So if you take that into account, then the reason why we are looking beyond turbo codes now for 5G is because we have now what we didn't understand, we didn't have then, is polar codes and spatially coupled LDPC codes that are capacity achieving with low complexity encoder and decoder. Okay? So that means that, for large n, these large block lengths, this code will outperform turbo code, and we can implement them, right? And even we see that they can work well for lower block lengths. So this n denotes block length here, okay? And we saw some curves this morning, right? And then they achieve better decoding throughput. Decoding throughput depends on your implementation of the decoder. So usually you look at the decoding throughput per chip area, and LDPC codes actually can perform much better. And then energy efficiency, we also saw, polar codes have better energy efficiency, especially for large block length where turbo code has to do a lot of iterations in decoding, or a polar code you don't have to do iterative decoding, so you gain. So for this reason, we're looking at both actually, but today I'm going to talk about polar codes. So rate compatibility is important for us. Why? So what do I mean first by rate compatible codes? I want to design a sequence of codes that have different rates, but they can be generated with the same encoder-decoder structure. So I don't have to have different encoder for every rate, okay? It's too complex, takes too much memory. So, and we want these different rates because we want to adapt to a time-varying channel, which is what we'll have. And one way to do it is to have hybrid RQ with incremental redundancy. Okay? So, what do we do in this case is, we send a code word, say the red one, that has higher rate that we could actually send. So what we get from the receiver is a NAC. Then we send additional, what is called usually parity bits. So this is now a new code word of lower rate. And then we again wait, and we repeat this process until we get ACK. So in this example, once we receive ACK, we stop. So the blue square would never be sent. Okay? So you send additional coded bits until you can decode. Okay? So that is good. And the typical way to get rate-compatible codes is to do what is called puncturing, we heard today, which just means that you will, you start with the code word of the lowest rate, which is mother code, and then you remove some of the bits, puncture them, you don't send those bits. And then if needed, if you get NAC, you send more of these parity bits. Okay, so this is what we need. Now, the question that we wanted to answer, and this is very related to what we heard this morning, is how to make it rate compatible. So, and it's not obvious for polar code, and here is why. If you remember, this is actually, we saw this same example this morning, is the way you form your polar code is that you fix your block length, right? You fix your n, in this example it's 8, then you determine your mutual information for these bit channels, these are the numbers shown here, and then you pick the best ones. So here I pick half of them because I want to make the code of rate half in this example. So the red ones will be my information set, and the blue ones will be my frozen set. Now, if I increase n, which is what I want to do with rate-compatible code, I have to recalculate the information set, okay, which is not that simple. So can we do something better? So, and here is the example of the performance. So this is the SNR, and this is the block error rate. So suppose I have a mother code that I puncture. Okay? So once I puncture, I will get the performance is this red curve. But if I, after puncturing, now recalculate my information set, this is the improvement I get. Or you can say, well, this is the loss. The red curve shows the loss because of the puncturing. Because my information set now changed. And it's not easy to calculate. So how do we do it? Okay? So let me show you our approach. So this is just notation. So C here denotes a polar code. It has length Ni. It's a rate Ri. And A is the information set. Okay? And okay, so the size of the set is such that, chosen such that I have the rate R. Okay. Now, so say you have a sequence of channels that have different capacities. So we have the graded channels that have rates R1 greater than R2, so forth. Then what we know, thanks to work by, this is PhD of Satish Korada in 2009, that if we fix the block length n, then we can construct a family of k-polar codes that have these rates. They are rate compatible. And they have the following property, that the information set of the code that has the highest rate, that's A1, is the superset of A2 and so forth. So this is the picture that shows it. So this is N, and now A1 is this information set of the highest rate code, so it's the largest. And then A2 is its subset, and then so forth, right? Each one is smaller because it's smaller rate. Okay, good. So this is nice. The problem here is that we have a fixed block length, right? But what we need instead for our hybrid RQ is we want to fix K, right? And then construct a family of polar codes that have different ends, and each code word of the shorter code word is the subset of the longer code word, right? So here is an example for N1 and 2. So I have the code word of length N1, and then I make my code word X2. So these are my parity bits that I want to send with hybrid RQ. That's why I want this kind of construction. So here is what we do in one slide. So I'll show you what happens for R1 and R2, and then it generalizes immediately. So R1 is greater than R2 as before. So I choose a polar code of rate R1 that I want with some length N1. So K is fixed, remember, that's the size of A1. Okay, so N1 I choose appropriately. Okay. Now, I want to form a rate compatible code that has rate R2 and same K, right? So it will have different N2. Okay. So what I do, I choose a polar code that is of same length N1, but it has lower rate, right? And then, hence a different information set. Now we know from the work of Satish or Corrada that A1 is a superset of A2, right? So this is all I did, as before. This is N1, this is my A1, and this is A2. And D, the blue rectangle, denotes the difference between the two. Okay. So now I take this D, and I encode it with a polar code that has rate R2, and it has some new length. Okay, so I'm using a polar code here and to encode a D. Okay. And I choose this N2 prime such that when I sum N2 prime with N1, it's exactly N2. Okay, this is what I wanted. And I want that because now I'm going to append this new code word to the first one. Because now these will be my parity bits for hybrid RQ. That's why I'm doing this. So this new code word is not polar. It's not a code word from a polar code. But that doesn't matter, because what I'm going to do at the decoder, if I'm decoding at a rate R1, then I just use my original code. I have this. This is a code word from the polar code, and I can decode. I'm at a capacity, right, if I have large N. Now, how do I decode at a rate R2? I do sequential decoding. So here is again what I have. This is what I received at the receiver. Now, I first decode just the D, and then I can decode using a polar decoder, right, because that's how I made it. So that's good. And now I insert these D bits as a frozen bits for my original code. Now this produces the second polar code that I formed, right, the code of rate R2 but length N1. And now I can decode A2 again using a polar code. So again, I'm at the capacity, and what I did, so this is what it says, I decode A2. So what I did, I decoded the difference, D, and A2, both using a polar decoder. So I decoded all set A1 at my rate R2. Okay, so this is how my decoder will work. Okay, so just to summarize, this is what I get. I get all the information bits, I split them, I have two polar encoders, right, for whole set, and then this will be for incremental redundancy if you want. At the receiver, I will first decode these bits, the D. I will put that as a frozen bits to my polar decoder of the higher rate, and I'll decode the rest of the bits. So what is nice is that I use the polar code at each step. So if I have N1 and N2 prime large enough, I'm at the capacity. And then this can be used for hybrid RQ. And I'm not showing you the curve because we are still working on it. So this is our idea. So in summary, I talk about two topics that we think are important for 5G. For multi-hop communication, I mean, we believe there will be multi-hop communication in 5G. Routing is not enough for high interference, that is high load, which is where we will operate the network. So we need something better. So we looked at noisy network coding, and we have a practical scheme for it. So that's it for multi-hop. And then for channel coding, we are looking at polar codes. We are looking also at DPCs, the spatially coupled, and today I talked about polar codes. So thank you.